Hey guys, welcome to the first virtual lab of Chem 150. Today we're going to be studying the behavior of gases, and we will use something called the ideal gas law. And we'll use this in order to try to calculate the molecular weight of the air that's all around us. So the ideal gas law, which is shown right here, is basically just a way of quantifying the behavior of gases. So while most gases that you'll experience in real life aren't technically ideal, we're going to act under the assumption that they are, at least for the purposes of this lab and for this class. So the ideal gas law is a way that relates the behavior of gases to certain quantifiable factors, such as in this case, the pressure, volume, the number of moles, and the temperature. So in this equation, pressure is always under the units of atmosphere. Volume, you'll always use the unit of liter. The N there is just for the number of moles, and then temperature will always be in Kelvin. And so that R value right there, that's the ideal gas law constant. And so it has a value of 0.082057. And if you take a note at these units, it's atmosphere liters over moles Kelvin. So that's a way for all of those units to be able to cancel out. And so what this means is if you are ever given 3 of these potential unknowns, you can then solve for the remaining unknown value. So in today's lab, we're going to be using this law to try to determine the molecular weight of air. So the way we'll do that is in part 1, we're going to measure the mass of 2 balloons. I've already filled them up for us. One balloon will have air in it, and the other balloon is full of helium. And then we will plug it into this, well, not this equation. We will then plug it into this equation to solve for delta M, which is the difference in the mass of those 2 balloons. And then we'll come back and we'll ultimately use this equation here, which is delta M is equal to the moles of air times the molecular weight of air minus the moles of helium times the molecular weight of helium. So in part 1, we're going to be solving for delta M, and then in part 2, we're going to solve for N, and then we'll be able to solve for the molecular weight of air, because at that point, the only variable that would be left is the molecular weight of air, because we already know the molecular weight of helium. It's on that periodic table. So to start off part 1's data, we're going to take the mass of these 2 balloons. So we will come on over to this balance. First, make sure to 0 it. The molecular weight of the air balloon, 2.68 grams. I'll come on over and record it here. And as you can see, I've already done those first 2 trials for us. I'm only going to illustrate the last one. The molecular weight of helium, looks like it's 1.27. So I'll plop that guy right here. So the data that we have for part 1 is that for the mass of the air balloon, those values are 2.67, 2.66, and 2.68 grams. For the helium balloon, it is 1.20 grams, 1.16 grams, and 1.27 grams. And I will leave it to you guys to figure out the averages. hopefully you can figure that out with the given values, and then once you know the average, you can then plug those values into here and here to solve for delta M, and then put that in your back pocket because we will use it again later. So that's part one. Part two of this experiment will require us to come back to this helium balloon, and we are going to be using the Logger Pro system. We're going to be using that Logger Pro system in order to calculate the pressure and the temperature of the balloon. And then we're going to be using something called an immersion method to calculate the volume. So first things, actually I'm going to do the volume first just because I want to get it before I undo the balloon. So the way this immersion method works is I'm going to completely submerge this balloon in the water, and as you can see, this bucket's completely full, so if any excess water is added, it is going to come out of this hole right here, and I will collect that volume, and whatever volume comes out will be equal to the amount of the balloon, which is what I added. So there's two ways this could go wrong. One, if this bucket isn't completely full, then the water won't start coming out right away, so that could impact the volume of the balloon. Another thing is if as I'm submerging it, I accidentally put some of my hand in there, that would cause more water to come out, and that would mess up the volume of the balloon. But let's just set. Okay, so I am now immersing the balloon, immersing, words. Okay, so now I will pour it into this graduated cylinder to try to get a more accurate volume. And it appears that the volume is 940 milliliters. Yeah, 940 milliliters. So I'm actually going to do 2 trials of that just to ensure the accuracy. So volume for trial 1, whoops. Volume for trial 1 was 940 milliliters, which is equal to 0.94 liters. Now I'm going to just do one more trial to ensure the accuracy of that result. Might need to refill the water a little bit. There we go. Okay, so now let's do that again. This is a lot easier to do in pairs because that helium balloon does not want to stay submerged. And it would be a lot easier if I could use both hands, but hey, we're working with what we got. Okay. Ooh, this is why we do 2 trials. I think the volume increased once I got the hang of things. Yes, it did. That volume is 1,200 milliliters. So, trial 2, 1,200 milliliters or 1,200 milliliters or 1.2 liters. Since there's such a big difference between those 2 numbers, I'm actually going to now do a 3rd trial just to really ensure we're getting you guys some accurate data. Okay, so for trial number 3. Okie dokie. Trial number 3. Let's pour that to this big old graduated cylinder. And yeah, that's a lot, still kind of different, but a lot closer to that first number, or I guess a little higher. So that one is 1340. So trial 3 is 1,340 milliliters or 1.34 liters. So the volume is going to be the average of those 3 values, so 0.94, 1.2, and 1.34, and I will leave that to you guys to calculate. So that is the volume of our balloon. Now we're going to take this balloon and bring it on back over to the computer where I have hooked up the Werner software. So we're going to assume that the temperature of the air in this balloon is equal to the temperature of the air in the room. So as you can see, that temperature is 20.4 degrees Celsius. So that means that that temperature value would be 0.4? Yes. It would be 20.4 degrees Celsius. And since that's based on equipment data, there's not really much room for human error, so I'm just going to do one trial for that. Now, the last thing we need to get is the pressure, which we get using this pressure sensor. Way to prop this guy up so you can actually see. Okay, cool. Well, struggles of a one-person crew. I will take this balloon. Okay, so now I'm going to hook it up to the pressure gauge. Just have to set this up to get the pressure reading. Okay, I also want to change the units. To atmosphere. Okay, so now let's see what the pressure is at. Okay. Okay, so the pressure that we're getting from that is a little marker. .970 ATM. Okay, so now we're ready to bring this all together. We have the pressure, 0.970 ATM, the volume, which you guys will calculate, which will be the average of these three values, 0.94 liters, 1.2 liters, and 1.34 liters. That's volume. We know R, which is just a constant, 0.082 057, and then the temperature, which is 20.4 degrees Celsius, which you will then need to convert to Kelvin. Once you have this, you will solve for N. N is the number of moles, and we will bring that N value and that delta M value that you calculated in part 1 and bring it all together in this final equation. So delta M is from part 1, N is from part 2, the molecular weight of helium is on the periodic table, and then you will solve for the molecular weight of air. Now, before you exit out of this, there's one more equation that you need to do, is the percent error. So percent error is the accepted value minus the experimental value, all divided by the accepted value times 100. And I will give you the accepted value. The accepted value for the molecular weight of air is 28.97 grams per mole. So that's how you do the molecular weight of air experiment. If it was difficult for you to get the data, or if I went too fast, I'm also going to post just a document with all of this data. Hope you guys are staying safe out there. Bye.